Today, I'm going to talk about how we can make containers lighter for the edge. Specifically, our focus on understanding what are the technologies needed at the edge in order to support emerging edge applications such as visual analytics, extended reality, autonomous vehicles. In cloud data centers, we could easily deploy these applications using prevalent container technologies. However, cloud-based deployment will not make it possible to meet their requirement for low latency. The question we explore with this work is what are the technologies needed to run this workload at the edge? We identified these three problems which make it impractical to simply transplant cloud-native technologies to the edge for these types of applications. I'll explain each in a little more detail. First of all, at the edge, computing capacity is relatively scarce, unlike in cloud data centers. Edge servers have very limited amount of resource, and this is the root reason where most problems of the edge come from. The techniques developed for the cloud with its many racks of server machines assumes almost limitless capacity and infinite scalability, and clearly, they will not be effective at the edge. Another problem is the bloat in application size. When thinking about the applications we are concerned with, each of them depends on some complex runtime, such as for machine learning or stream processing and analytics. In addition, many of them rely on hardware accelerators, particularly in order for them to be able to perform sufficiently well with a limited resource footprint. These requirements significantly change the image size requirement for these applications compared to the requirement of images for simple tasks requiring just basic OS functionality. Let's say someone needs to deploy an application with a TensorFlow package, then a few hundreds of megabyte binary should be passed over the network. In the edge context, this doesn't make sense at all. Moreover, if the image includes the CUDA support, the situation becomes far worse. The size of TensorFlow or PyTorch with CUDA support exceeds a few gigabytes. This makes it impractical to deploy such applications at the edge on demand. Finally, the performance requirements of the edge workload we target demand responsiveness from the edge, which ideally expect fast application launch time. Unfortunately, the responsiveness of current container launch techniques is too slow for applications we target. Consider this timeline, which illustrates how long it takes to launch a container with a TensorFlow-based application. We perform this on a typical Xeon server platform, which is quite reasonable for some of the edge systems being considered. Here the container managers takes around 2 seconds to run a container, and on top of that, importing the TensorFlow package takes another 2 seconds. What this shows is that heavy runtimes that are needed by modern applications not only cause image bloat to occupy the network bandwidth and increase the resource pressure, but also contribute to the container startup indirectly through the package import time. Common applications such as data analytics, image classifications necessitate heavy runtimes, so the situation is bad and continues to get worse going forward. In this situation, one approach developed in recent work to improve container launch time is to rely on container checkpoint restore techniques. However, checkpoint restore exacerbates resource pressure. It increases memory pressure by nature. It can help using additional memory or disk space to create and store the checkpoint. The figure on the left hand shows that the image restored from a checkpoint consumes more memory than the cold boot case, and also it cannot solve the image bloat. Another approach is to use a single long-running monolithic container to host all application instances. This does reduce the resource pressure on the edge and does not require on-demand launch and initialization of the runtime. However, This incurs another problems. Developers need to adapt to a new interface to package and deploy applications, and also, this naive solution does not leverage existing container-based infrastructure. And we don't want to lose the benefit from the containerization. This naive solution without containerization is not really a solution. We are seeking opportunities somewhere between no container solutions and monolithic containers. We wanted to minimize the resource pressure, and we wanted to make startup quick, and we wanted to make applications as compact as possible, while retaining all the good things on containerization, such as well-known interface and its own packaging platform. To achieve that, we suggest the concept of shared backend. You can see the ordinary containerized application from the figure. We're going to separate this into these two. The shared backend will include the heavy runtime stack. It will be a long-running edge service, and as such, its launch time will not be exposed in the critical path of launching application. Applications will continue to be deployed as containers, retaining the benefits of application packaging and distribution. The runtime component will not be a part of the application container images, allowing us to achieve lightweight application containers. They will share the backend runtime, thereby operating with a reduced resource pressure compared to each application instances requiring a separate runtime instances. We prototyped this approach in a system we call Pocket, a new lightweight system to support edge computing. Pocket aims to achieve aforementioned goals by splitting containerized application into two parts, or service container and application containers. With the Pocket, one service entity serves multiple application entities. In result, application entities themselves may contain only essential workload-specific data, and it leads the application to have less resource footprint. The Pocket programming model that we proposed for the edge environment looks like this. The system consists of three components: service container, application container, and the communication between them. The basic mechanisms of this system is that the workload run as usual, and if they need special support or heavy runtime, they exploit the service backend rather than instantiating the library themselves. In order to make this design possible, three design elements should be realized. 1. Workload isolation. 2. High performance IPC. 3. Full concurrency and dynamic resource scaling in runtime. In the current implementation, we partially compromises on conventional notion of isolation in order to improve resource efficiency, but we still guarantee the basic isolation semantics like namespace isolation. Let's move on to evaluation part in order to verify if this design is feasible and to observe the meaning of this design implies. In this experiment, we measured end-to-end latency of a complete path of the machine learning application lifecycle from building the model to processing the query and returning the result. We used the YOLO version 3 TensorFlow implementation as our benchmark here. This is the evaluation that we conduct in order to examine if Pocket has less resource footprint compared to the monolithic case. You can see that as the number of instances rises, the resource footprint of solutions based on a monolithic container linearly increases steeply. The resource footprint of Pocket increases in around 50% slower manner compared to the monolithic containers, which result from the warmed-up service entity. And also, Pocket contributes to performance improvement. Despite using fewer resources, Pocket achieves better application performance, in this case lower inference latency. The table shows the comparison between the Pocket and the monolithic case. As the number of instances goes up, Pocket achieves lower average latency. Pocket doesn't degrade the performance of the applications, but it speeds them up thanks to the caching. Finally, Pocket allows to realize lightweight containers with small image sizes as intended. A key to achieving this is to maintain a lightweight communication runtime. We have multiple implementations with different communication mechanisms. The table shows that Pocket SSH achieves agile startup compared to monolithic case, but one with heavier communication methods does not. What we can learn from this table is that lightweight communication are needed. In summary, with Pocket, we explore an alternative design for the application stack at the edge. We highlight several problems associated with using cloud-native hosting infrastructure based on monolithic containers at the edge. With Pocket, we present a path forward that combines the benefit of leveraging container-based infrastructure while achieving better resource efficiency and scalability. We identify several technical challenges that must be addressed in fully developing a solution like Pocket related to lightweight IPC, support for concurrency and isolation. Our prototype integrates early implementation of these solutions, which demonstrate the feasibility and the utility of the approach. Thank you.